Okay, so it seems that we have over 100 attendees now, so we can start. Thank you everyone for joining us today to this weekly Polariton chemistry webinar series. My name is Luis Angel Martinez, and I've been honored to host today's webinar speaker, Professor Stéphane Kéna-Cohen, here present from Polytechnique Montréal. So before listening to our speaker's talk, allow me to briefly share some information regarding the schedule and mechanics of the webinar. So as you may know, this weekly webinar series takes place every Wednesday at 9 a.m. Pacific Standard Time. Importantly, you must sign up for each webinar you wish to join at the link shown here, which you can also find in social media. So make sure you follow us for reminders and updated information. Also, for convenience of everyone, we have set up a YouTube channel where we will be posting the recordings of webinars in case you miss one and want to watch it later. So finally, let me quickly explain the mechanics of this webinar. At this point, probably most of the audience is already familiar with Zoom controls, but for the sake of putting everyone on the same page, I will briefly review them here. So during the talk, you feel free to use the raise hand button to ask questions directly to the speaker. So when you raise your hand, I will interrupt the speaker and I will enable your microphone so that you can publicly ask your question. And you will also see the Q&A chat where you can type questions you may have during the talk. And at the end of it, and if time permits, these questions will be addressed by the speaker. Finally, you can use the chat control to send messages to panelists on the audience in case you want to discuss anything. And importantly, for the sake of time, only questions in Q&A and those requested by raising hands will be addressed. So with nothing more to add, let me introduce our today's speaker. Stéphane Kéna-Cohen is an associate professor in the Department of Engineering Physics at Polytechnique Montréal and the Canada Research Chair in Hybrid and Molecular Photonics. He obtained his PhD at Princeton University under the supervision of Stephen Forrest, where he demonstrated the first organic Polariton laser. He then spent 4 years at Imperial College, where he was a junior research fellow, working with Stefan Meyer and Donald Bradley. There, he worked on nanophotonics as well as strong light matter coupling and performed the first studies of Polariton nonlinearities in organic microcavities. In addition to continuing work on strong light matter coupling in Canada, his group also worked on optoelectronics. In the last year, his group has demonstrated world record efficiency near infrared OLEDs, as well as the first mid-infrared LEDs based on 2D materials. With that being said, now I concede the microphone and the screen to Professor Stéphane. So let me. All right.
Okay, great. Okay, so thank you, Luis, for the introduction. I'll just share my screen. Okay, fantastic. So thanks, Luis, again, and thank you, Joel and Wei, for organizing this series of webinars. So my talk today will be a bit different from the usual research talk in the sense that instead of presenting the latest results, I will follow a recent review that I wrote alongside Jonathan Keeling on BC of organic polaritons, and we'll try to present really an overview of where the field is, what the important questions are, and where the future is heading. So given that I've got quite a long presentation, I thought I would start by acknowledging all those contributors in the slides that I have prepared. In particular, Fabio Baracciati and Kostas Daskalakis, two excellent students who've done a lot of the work I'll be showing and who have now moved on to bigger and better things. Theory collaborators from the group of Michał Matuszewski in Warsaw, as well as the group of Giuseppe La Rocca in Pisa. And if I get time to talk about superfluidity, this was work that was done in collaboration with the group of Daniele Sanvito and his excellent team. And then finally, of course, Jonathan Keeling for co-writing the review and support for quite a bit of this work, which started at Princeton with Steve Forrest and continued on at Imperial College with Stefan Meyer and Donald Bradley. Okay. So the type of system that we're interested in is shown schematically here. So these are your typical collective strong coupling microcavities where we have an ensemble here of n molecules placed within an optical cavity. These molecules for now will be simple two-level systems. They have a ground state, an excited state, and some resonant frequency omega 0. And those molecules will be resonant with one of the longitudinal modes supported by the cavity, also frequency omega 0, and that mode we'll consider as being either empty or occupied by a single photon. And light matter interaction here at the single molecule level is described by this coupling constant G, which is related to the transition dipole moment of one of these molecules. Now, the situation we're interested in is the collective strong coupling, where the collective light matter interaction strength G square root of n is larger than dissipation in the system. So this is a regime where light matter interaction cannot be treated perturbatively, and we have to diagonalize light matter system to describe the dynamics. So here, gamma and kappa are dissipation rates. Kappa would correspond to the rate at which, for example, light leaks out of the microcavity due to the finite transmission of one of the mirrors. And gamma describes dissipation due to the matter component. This can be non-radiative loss. It could also be the emission of a photon in some other mode other than the longitudinal mode that we're considering here in the model. Okay, so in the single excitation subspace, this full Hamiltonian is very simple. We have on this first column the situation where we have a single photon, but no molecules excited, and then no photon in the mode, but the first molecule excited, the second molecule excited, all the way to the nth molecule. And if we diagonalize this Hamiltonian, we end up with two bright eigenstates. Those we will call the upper polariton and the lower polariton. They're split by this collective Rabi splitting, square root of n times g. And since we diagonalize an n plus 1 dimension Hamiltonian, we of course have n plus 1 final states. The missing states are these dark states. We have n minus 1 dark states, which are in the gap at the bare resonant frequency omega 0. So what I should highlight is that these polaritonic states are symmetric and anti-symmetric linear superpositions of one cavity photon with the totally symmetric excitation of the molecules. So the state where all of the molecules are excited in phase, but with an amplitude 1 over square root of n. Okay, and these dark states in a Fourier basis could be considered to be all of the collective molecular states with k vectors other than k equals 0. But of course, these are degenerate, so you can choose whatever representation you prefer. And in this system, the ground state is unmodified. So given that we want to describe BC, we need to go a little bit further because here we only have a single polaritonic state, but we want to consider the occupation of a multi-energy level system. And for this, we need to consider the various photonic states which exist in the system. So these planar microcavities have a number of optical states. All of these are characterized by their in-plane momentum. Here, of course, in-plane momentum is conserved because the system is translationally invariant in plane. And we can parameterize the different photonic states as a function of k parallel. And the dispersion is given by this equation here on the bottom. You see here that in this system, because we have a fixed cavity length, the z component of the momentum is quantized. So this is fixed, and the dispersion is nearly parabolic as a function of the in-plane momentum k parallel. So we have a system where photonic states follow this parabolic dispersion relation. Our two-level system here, which is our exciton, has an energy which is independent of k parallel. And then if you turn on light-matter interaction, you end up with this collective Rabi splitting as before here at the degeneracy point, but you also end up with many more polaritonic states which are parameterized as a function of their in-plane momentum k parallel. So we have many polaritonic states. Each of these can be described as some linear superposition of our cavity photon with some photon component alpha and some collective electronic excitation with some exciton fraction beta. Okay, so this is for planar microcavities. I should highlight, although I won't be talking about other photonic systems, that very similar physics occur in dielectric waveguides and plasmonic lattice resonances, dielectric lattice resonances, but for condensation, these planar cavities tend to have a number of advantages. Okay, just as in the single mode example at the beginning, we also have a large number of dark states in the gap. These tend to outweigh the number of photonic states by about a factor of 10 to the 6 to 10 to the 7 to 1. So the presence of these dark states was first highlighted by Marina Listinskaya and Vladimir Agronovich in some earlier works. And in this book chapter, we have a simple calculation to estimate really the ratio of these dark states. So because of their large number, they tend to play a very important role in the dynamics of these polaritonic systems. Okay. Another interesting feature is the fact that this lower polariton branch has a very small effective mass, an effective mass which is on the order of about 10 to the minus 11 times the mass of a rubidium atom. And this low effective mass is really the feature which garnered quite a bit of attention at the beginning of this field, because it puts forward the prospect of achieving Bose-Einstein condensation of polaritons at an elevated temperature. Okay, and just to drive the point across, I also have this slide to show you schematically what a polariton really looks like in space. So of course, if we pick some momentum, we have this plane wave excitation with a photon content, which is simply representative of the field of the photonic mode. And alongside this, with the same k vector, we have our material excitation, which also is coherent across the lattice. Now, in most of these organic systems, we have quite a bit of orientational, energetic, and positional disorder. So what this tends to do is to localize the excitonic component of this polaritonic mode in space. And this was first discussed by Agronovich, and then nicely demonstrated in numerical simulations in this work by Michetti and La Rocca in 2005. And what they found is that in regions of the dispersion relation, where the dispersion relations are relatively flat, so non-dispersive, states in these regions tend to be quite localized.
Professor?
Yes.
We have one question from the audience.
Yes.
So, yeah, Gilab, you can talk now. Gilab, enable your audio, your microphone.
Yeah, can you hear me now?
Yes.
Yeah, sorry. So my question is, what is the meaning of a wave function that is delocalized in the photonic part, but is partially localized in the excitonic part? Does that not localize the whole wave function?
So what you tend to find is that because the disorder is coming from, so the wave vector of the photonic part is fixed, and this is determined by the field distribution. But what disorder will do, because the disorder is only in the excitonic part, is to localize the excitonic part in space. And this is really nicely highlighted actually in the second reference if you want to see an example of a 1D simulation where you just diagonalize this Hamiltonian, adding disorder to the excitonic component. So you'll find that if you take the K-space solutions, and for your transform or you do it directly in real space, you end up with localization in real space, especially for the excitonic component.
Okay, thank you.
Actually, we have one more question. So, Joel?
Sorry, Stéphane, but isn't it the case that if you have localization in the excitonic part, you also need to add like a wave packet for the photon part so that it also localizes the photonic components of the wave function? So like both the excitonic and the photonic part remain quasi-localized?
So I think that this is, so maybe what's a little bit misleading here is that if you look at the influence of disorder, it makes more sense to do this directly in real space. And what tends to happen is that the photonic part still remains relatively delocalized. So
for every eigenstate, you don't really create like a wave packet also of different K modes for the photon?
So you tend to create a localized wave packet in space for the exciton part, but the photon part will tend to be much more delocalized than the excitonic part.
Okay, I need to think about that. Okay, thank you.
Okay, so I'll continue. So those are polaritons. I'm assuming that the audience is mostly from the chemistry side, so I'll say a few things about BC first in 3D. So given that these polaritons are bosons at low density, their occupancy is determined by the Bose-Einstein distribution, and the number of excitations in the system or the number of particles for bosons is given by the integral of this Bose-Einstein distribution times the density of states. And in 3D, the density of states scales as square root of the energy. So when we carry out this integral, as you move the chemical potential higher and higher, you eventually reach a limit for the maximal number of particles that can be sustained. And beyond this, what Einstein showed, of course, is that the remaining particles have to end up in the condensate, which will be the lowest energy state of the system. So this critical density at which you can no longer fill the excited states is proportional to a power of the effective mass of the particle and the temperature. So a very low effective mass leads to a very low critical density, or equivalently, for a fixed number of particles, you have a very high critical temperature. So schematically, what happens is that you have some number of states which you need to fill. As you continue to add particles, you move the chemical potential upwards. Whoops, and when you reach the lowest energy eigenstate, you form a condensate, and the chemical potential stays clamped near this energy. And the wave function of the fully condensed state would simply be some product state of every single particle in this lowest energy eigenstate. Another important feature of the condensate is the fact that beyond threshold, you have the appearance of off-diagonal long-range order. So if you consider the spatial correlation function, which is basically telling you about the phase relation of the condensate at 2 points in space, even at very long distances, you have a non-vanishing value of this correlation function, and that value actually corresponds to the condensate density. So N0 corresponds to the number of particles that are in the condensed phase. And if you were to normalize this, actually it would be the fraction of condensed particles. In 2D, the situation is slightly different. So we know from the Mermin-Wagner theorem that in principle in 2D there is no possibility for spontaneous breaking of a continuous symmetry for an infinite system. Also, if you just look at this relation, which we use to predict the critical density in 3D, the simple argument here doesn't hold. We can always solve for any given number of particles and find the corresponding chemical potential in 2D. But nevertheless, if you look at the first order coherence, you find that as you increase the number of particles, once you reach quantum degeneracy, which corresponds to the situation where the de Broglie wavelengths of the individual particles start to overlap, you have a qualitative change in the behavior of G1. So the coherence function goes from Gaussian to exponential. So you have an increase in the coherence length. And in the systems we'll be considering, we typically will consider a finite size system. So if you have a finite size, then you can have a condensed regime. And this more or less corresponds to the situation where the correlation length is equal to the system size. This is very close to the density where you would reach quantum degeneracy in most cases. And we also have interactions. So interactions also play an important role in 3D. And in 2D, they can lead to a superfluid state where the decrease in the first order coherence becomes algebraic. And this occurs due to the Berezinski-Kosterlitz-Staulis mechanism beyond some critical density, which is related to the strength of these interactions. So this kind of equilibrium physics have only recently been observed in inorganic microcavities and only in the best microcavity platforms available, which are those fabricated in the group of Lauren Pfeiffer at Princeton, using those systems which have Polariton lifetimes of several hundred picoseconds, so much longer than thermalization time in the system. David Snoke and Keith Nelson showed that if you look at the occupancy of the Polaritonic states as you increase the Polariton density, you can get a near perfect fit to a Bose-Einstein distribution where the only parameter which is changing is the chemical potential. So this really reproduces up to condensation, equilibrium BC physics very nicely. And more recently, the group of Daniele Sanvito has also shown that in these same systems, as you increase the particle density, if you measure the value of the first order coherence function in space and in time, in both cases, you find a value of alpha, which is this algebraic decay exponential equal to about 1/4, which corresponds very nicely to the anticipated BKT type of physics. So what are some applications of these Polariton condensates? One important application which is being studied is the use of Polariton condensates to do quantum simulation using analog Hamiltonians. So the idea here is that you map out some Hamiltonian of interest onto a lattice, and then by pumping the system, you're able to identify the ground state, and possibly if you can time resolve the evolution, also map out some of the temporal dynamics of that Hamiltonian. A very closely related idea was put forward by Natasha Berloff a few years ago, which is to map different problems, not problems necessarily from condensed matter physics, but any problem to some Ising, or in this case, XY Hamiltonian, and then use the same idea of using condensation for the minimization problem. So letting the condensate find the global minimum of the lattice which you've implemented to map out the minimization problem that you're interested in. Okay. In the context of organics, one of the most interesting prospects for Polaritons is, of course, to simply realize very low threshold sources of coherent light. Electrically pumped organic lasers continue to be an outstanding challenge in the field. And if Polariton lasers can have a threshold which is several times lower than a comparable organic laser, then this would allow for electrical injection potentially. Okay. Unfortunately, yes.
We have one more question from the audience. Well.
Oh, okay, sorry, Stefan, maybe just to clarify to the audience. Okay, so I think you have told this to me before, but can you explain again Why is it better to use condensates for quantum simulation rather than just the polaritons at low excitation in the low excitation regime?
Yeah, so actually that's a very good question. Just to be clear, so on the left, everything I've shown is just linear regime. So effectively, all this is doing for you is a band structure calculation. So that's not terribly interesting. What is more interesting is finding the overall ground state of that Hamiltonian, and for that, you use condensation. So the idea is that stimulated scattering should take you to the global minimum.
Okay, but in principle, even in the linear regime, you should be able to do some quantum simulation with these polariton systems, wouldn't
Correct.
you?
So everything which is done here is linear regime on the left, and you can just do angle resolved photoluminescence and measure directly the band structures.
Okay, thank you.
Okay, so we had those slides a few slides ago on the work from David Snokes' group and the work from Daniel Sanvito's group on equilibrium BC physics. In organic systems, we're typically very far from this regime. So the reason for this is that most organic microcavities that have been used for condensation have very short polariton lifetimes on the order of 300 femtoseconds or less. I believe the best demonstration has a lifetime of 1 picosecond. So these timescales are much shorter than typical relaxation and thermalization times in these systems. So the dynamics of these polariton condensates are out of equilibrium. And two approaches have been used to model organic polariton condensation. One is to use a simple rate equation, so a kinetic model. So in this case, we assume that the normal modes are fixed, and scattering rates between initial and final states are just calculated using perturbation theory. This is what we did, for example, in the case of modeling condensation in Anthracene. And in this sort of model, we would have some pump term which populates initially our reservoir of dark excitonic states, and then these scatter to different states along the lower polariton branch, and you can also have interbranch scattering. Generally, the dominant contribution would be the one coming from dark states directly to the bottom of the branch, and in this kind of model, the condensation threshold effectively corresponds to the situation where your pump is such that the net scattering to k equals 0 is equal to the loss rate from k equals 0, which is just given by the polariton lifetime. More sophisticated approach, and certainly one that would be more pertinent to Anthracene, where you have strong exciton-phonon coupling, is to include vibrational coupling explicitly in the Hamiltonian. So this involves the use of the Tabis-Cummings-Holstein model, which has been used by Jonathan Keeling, Felipe Herrera, Frank Spano, and Johannes Feist to describe luminescence and to study the states of excited molecules in optical microcavities. And here what we have is the vibrational coupling term, which accounts for exciton-phonon coupling via the Long-Rees parameter. And by using this Tabis-Cummings-Holstein model in the master equation, which accounts for both pumping and dissipation, the Keeling group was able to calculate these phase diagrams for condensation, as well as conventional organic lasing in a nice uniform fashion. And the overarching conclusion from that work is that polariton lasing allows you to obtain coherent light emission at low thresholds, particularly in regions where you have high absorption, where photon lasing would be greatly inhibited. So this is an example in a regime of positive detuning. Omega C is the cavity frequency. Here the exciton frequency would be equal to 1. This red line shows the phase boundary for conventional lasing, and you can see that you have regimes of polariton lasing at thresholds. This is pump power. At thresholds much lower than that necessary for photon lasing. So this is a nice perspective. This is all single photon mode, but this theory was very recently extended to the multimode case. Okay, so what are the experimental signatures of polariton condensation? So in the power dependence, what we see when we look at emission coming from k equals 0, which is normal incidence, is a very sharp threshold. This corresponds to the onset of stimulated scattering to that final state. Because of stimulated scattering, you also expect a collapse in the PL lifetime. We have increased temporal coherence, increased spatial coherence at threshold. So we see this in the reduction in line width and the collapse in the k-space distribution of polaritons. We can have, in some cases, spontaneous polarization. So this is shown here for a specific material called TDAF. So below threshold, emission is completely unpolarized. When we cross threshold, we have polarization along the pump polarization direction. Here's that threshold and the power dependence, the reduction in line width. And in some cases, we also have a blue shift, and the blue shift is a signature that you have some form of nonlinear interaction. Now, an important point is that all of these first few bullet points are really characteristics of any type of laser, whether it is a photon laser or a polariton laser. The blue shift is a nice signature that you have some strong nonlinearity. Often this is true for polariton lasers, maybe not so much for photon lasers. And of course, polariton lasing itself implies that you must have some significant exciton fraction in the mode, and that when you pump at a density such that you do not have a transition to the weak coupling regime. Okay. So the first material used for polariton lasing was single crystalline anthracene. Here on the left, we have the crystal structure of anthracene. So in a single unit cell, we have two inequivalent molecules. The interaction between these molecules leads to a Davidoff splitting of the low-lying exciton band. And the lowest lying band is this band which is polarized along the B direction of the crystal. And if you look at the dispersion relation, because of these vibronic replicas, you actually end up with a manifold of polaritonic states along the B direction. So we have this lower polariton branch, a few middle polariton branches, and an upper polariton branch. One of the reasons anthracene was first studied was really because of this worry that localization in space somehow prevented polariton lasing. It turns out that's not the case, but it was a strong motivation for looking at single crystalline materials to realize condensates. And then condensation in this material happens when the lower polariton branch minimum is exactly one vibrational energy away from the reservoir, which is here at this 0, peak. So in the polariton spectra, we don't see anything here, but we know this is where the bare resonance lies. And then when you pump the system at high power, you find this threshold from a sublinear regime, just because you have very, very strong bimolecular annihilation, to a superlinear regime, as well as a collapse in line width, a collapse in the k-space distribution, and a collapse in the lifetime once you cross threshold. An interesting feature in anthracene, which is rather unique to the system, is also the fact that when you cool, so all of this is at room temperature, when you cool down, you have also a drastic reduction in the lasing threshold. And then the other thing I didn't mention is that for anthracene, the blue shift is rather negligible. So as we cross threshold, we have only a tiny blue shift, less than a line width. So interactions seem to be relatively weak in this system. So this is a plot of the power dependence in an anthracene microcavity as you cool from room temperature to 12 Kelvin, and we find a reduction of about 10 times in the threshold. Now, to somebody coming from the inorganic community, this would be relatively obvious, but most organic lasers do not show a temperature-dependent lasing threshold. And the reason for this is simply because most of these laser dyes have luminescence yields that are already near 100% at room temperature. The PL efficiency of anthracene is more than 60%. So when you cool down, you don't expect a large reduction in threshold. So this is something interesting, which may be due in part to the reduction in line width, but still I would say an outstanding question in terms of understanding this in detail. A few years later, Polariton lasing was shown in two amorphous materials. Our work focused on this trimer of methylphenylfluorine called TDAF. Below are just images of the K-space luminescence below threshold and above threshold, where you have this collapse
Professor, sorry.
near K equals 0.
Sorry, Professor.
A blue shift. Yes.
We have one question from the audience. Joel?
Okay, so, sorry. Okay, I just want to also to clarify. Okay, so the blue shift is just due to the bleach of the ground state, or is it more other types of interactions between the polaritons?
That's a very good question. So I'll get to this, but in all of the systems that I know of, it is only due to a bleach of the ground state.
Okay, thank you.
Okay. For condensates. There's also a different case, which is, for example, our work on third harmonic generation, where there the chi3 is really due to the intrinsic chi3 of the bare material, but not due to a bleach of the resonance. But here, near resonance, the dominant contribution is coming from the ground state bleach. I'll come to that in a few slides. Okay, great. So this material here was thermally evaporated. MELPPP, which is a ladder polymer, was spin coated in very similar physics. So you see this collapse in K space, a blue shift as well as you cross threshold. And this blue shift is a signature that you have some type of interaction. And as Joel just mentioned, in the case of these materials, that interaction is coming from the fact that you have a ground state bleach. In TDF, we also were able to see the spontaneous polarization of the emission. And this wasn't possible in anthracene because the anthracene emission, due to the crystal structure, is always polarized. So there was no chance for this spontaneous polarization to be observed. Okay? And in these two systems, also the spatial coherence was directly probed. So beyond the reduction in K space that tells you have increased spatial coherence, these were also measured in real space using interferometry. Okay, so the way this is usually done is using either a Mach-Zehnder or a Michelson interferometer. The Michelson interferometer was used for TDAF, and this is a Michelson in a retroreflector configuration. So that is to say, we've taken one mirror, replaced it by a retroreflector, and what we do in the experiment is image the condensate onto a CCD camera, and then take an image of the condensate, flip it along X and along Y, overlap it with the unflipped image to create an interferogram. And in that interferogram, each point at, let's say, R tells us about the phase coherence between this point and the point at R prime, which is central symmetric. So R prime here would be minus R. And by moving a delay stage, we can quantify the visibility of these fringes and quantitatively extract the degree of first order coherence, G1. Okay, so this was done in TDAF as a function of the pump power. What you find is that G1 increases in both space, so coherence length, and in the absolute value as you increase the pump power. And at power of about twice threshold, the coherence length is nearly 38 microns, which is much larger than the pump spot itself. In this sort of situation, you can also get the temporal coherence for free. So here, the temporal coherence, which you get from looking at the decrease in visibility of the Michelson, just like you would use a normal Michelson, is on the order of 1 picosecond. And this 1 picosecond is simply the duration and time of that condensate emission burst, because in all of these experiments, we always pump impulsively. So we pump with a short pulse, we populate a reservoir of dark excitons, these scatter to populate polaritonic states, but once that reservoir is depleted, there is no more condensate emission. So this 1 picosecond corresponds very closely to the calculated duration of that condensate emission burst. Okay. Recently, so actually just this year, there was work from the group of Sven Hoffling using nanosecond pumping. So now the pump duration is no longer impulsive, but much longer than the relaxation dynamics in the system. So you can probe the intrinsic condensate coherence time. And they found that coherence time in this microcavity based on a protein called M-cherry was as much as 156 picoseconds. So this is very interesting because it also allows you to do quasi-CW type of experiments. Okay. Other materials that have been studied are small molecules in a matrix, in particular this Bose-Einstein class of molecular dyes. These have the advantage of being very easily fabricated simply via spin coating. Fluorescent proteins like M-cherry or green fluorescent protein has been studied by the group of Malte Gaither as well as the group of Sven Hoffling. And materials very similar to TDF, so other oligofluorines. So TDF had this trimer of methylphenylfluorine. The polymer, PFO, has been studied, as well as pentafluorine, F5. And all of these show polariton condensation. And so we have this nice summary table from the paper in terms of highlighting the properties of these different systems. And the lowest thresholds are observed in these fluorine systems. So TDF, pentafluorine, and PFO show polariton lasing thresholds on the order of about 10 to 20 microjoules per square centimeter. And both protein systems have the advantage of showing very stable condensate emission under nanosecond pulsing, which is interesting for several applications.
Professor?
Yes.
We have one question from the audience. Yeah, so Randall, you can talk now.
Hey, Stefan, this is Randall Goldsmith at UW-Madison. I have a question about this slide. So in the fluorescent protein systems, the chromophores are well insulated from each other. There's no direct electronic communication between the chromophores. In the polymeric systems, I think there is a lot of direct overlap and direct interactions. With the Bose-Einstein systems, where they're in some transparent polymer matrix, whether there's interactions or not, I think is a function of just the density of the chromophores. Can you comment on the need for these direct interactions in forming the condensate?
Yeah, so that's an excellent question. And I would say that in all of these systems, except for anthracene, those interactions are irrelevant. So these really act like an ensemble of isolated molecular systems. Okay, so in Bose-Einstein, typically doping densities are between 1 to 5%. So the molecules are very well separated. In TDAF, we have this huge Rabi splitting because we use neat films. But actually, if you do a calculation of the anticipated molecular structure of the amorphous film, you see these molecules are very twisted, and the dipoles are well separated. And in fact, if you look at the solution properties and the thin film properties, you see that they're very similar. So this tells you that in the thin film, aggregation and exciton-exciton interaction doesn't play an important role. So these are acting in almost all of the cases, I would say, except for PFO and anthracene, as well isolated chromophores.
Thank you.
We have one more question. Bin, go ahead.
Hi, this is Bin Liu from City College of New York. My question is, for organic materials, it seems like people always use very large negative detuning in order to achieve polariton condensation. So how about the positive detuning? And because for inorganic materials, it seems like positive detuning can be easier for achieving, equilibrium Bose-Einstein condensation. What will happen, to the organic material?
Yeah, so that's a good question. So typically in inorganic materials, and this depends a lot on the actual inorganic system that you're considering, but normally the lowest threshold will be somewhere between 0 detuning and maybe minus the Rabi splitting over 2 in terms of detuning. In organic systems, the problem is that if you go to 0 detuning, typically the polariton lifetime increases dramatically, just because you have so much inhomogeneous broadening. And the lasing threshold is directly related to the polariton lifetime, because you need to have a scattering rate which exceeds that lifetime. So the trick people use to increase the polariton lifetime in organics, where you have large inhomogeneous broadening, is to move to more negative detuning. So in TDEF, for example, the Rabi splitting is about 600 MeV, and we typically are operating in a regime where we have a detuning of maybe minus 300, minus 400 MeV. So a little bit more than half of the Rabi splitting away in terms of detuning. And this is really because of the lifetime. So if we approach 0 detuning, the lifetime of the polariton goes down because of the broadening, and we see a very similar increase in the lasing threshold.
I see, thank you.
Okay, so that's threshold summary. So now I wanted to say something about nonlinearities, and really it's going to be repeating what I just mentioned to Joel. So in von Neumann excitons and inorganic polaritons, this has been studied extensively. So there, the nonlinearity comes from 2 contributions. One is due to the direct Coulomb interaction between excitons. So excitons are neutral, but of course these are composed of electron hole pairs. And if you have this system with 2 excitons, the total wave function should be antisymmetric with respect to the exchange of 2 of these identical carriers. And this leads to an effective Coulomb term, which is really not present in these organic materials, so we can ignore that. The other contribution is that due to saturation. So in inorganics, you have phase-space filling. So as you increase the density of excitons to a density which is becoming comparable to the inverse of the exciton Bohr radius, you start to have a reduction in the oscillator strength. So N is the exciton density, and S is what we would call the saturation density. This reduction in oscillator strength leads to a reduction in the Rabi splitting and an effective blue shift of the polariton resonance. We effectively have the same in organics, but in organics, this is coming from a reduction in the ground state occupancy, so a ground state bleach. And molecules here would be the total number of molecules, N would be number of excitations in the system. And given that the collective Rabi splitting scales as square root of N, where N would normally be the ground state occupancy, which here has been sort of relabeled N molecule minus N, as you increase the number of excitations, you reduce the Rabi splitting and you create a ground state, and you create a blue shift of the lower polariton branch. In the way we model the dynamics of the condensate in a way that allows us to include this nonlinearity is using the Gross-Kutaevsky equation in analogy to what you would do to model an atomic BEC. And one change to the usual Gross-Kutaevsky equation is that we will also use a term which accounts for pumping and dissipation of the condensate, as well as a term which accounts for interaction with the reservoir. Okay, so this is a nonlinear Schrodinger equation. This G psi squared term is the nonlinear term, where G is the effective polariton-polariton interaction strength, nothing to do with the coherent coupling G from earlier. And R is the number of dark state excitons, so the reservoir density. G tilde is the interaction strength between our polaritons and this dark exciton reservoir. And here, the pump term is given here. W is the scattering rate from the reservoir to the condensate. And gamma LP is simply the condensate or lower polariton lifetime. So this Rose-Katievsky equation is combined with a simple rate equation which describes the occupancy of our dark states. So these dark states are populated by a laser pump. They decay with some lifetime. We might have bimolecular annihilation, so you can include that. And this is scattering from the dark states to the condensate. Okay. So then an important question is, how strong is this nonlinearity G, and how strong is the G tilde? So if we assume that the only contribution is that which is due to the ground state bleach, just from the Rabi splitting and the molecular density, so nothing else, you can estimate the value of G tilde. For TDF, we estimate something which is on the order of about 7 times 10 to the minus 4 micro EV micron squared. So you can think of this as the blue shift per polariton density. And if you just take this number and try to reproduce the blue shift as a function of pump power without any fit parameters, and this is just taking the molecular density, you find that qualitatively it agrees relatively well with the measured blue shift, which is given here by these triangles. Now this model only works until this point here, beyond which in these polariton condensates, the reservoir density gets clamped at the threshold value. So this is just like in a regular laser. So reservoir density gets clamped, so the blue shift due to the reservoir, which is this G tilde, no longer plays a role. And in this beyond threshold part of the blue shift, this is due to polariton-polariton interactions. So from the experimental data, you can also get the G value, and we find from the blue shift above threshold that G is on the order of about 10 to the minus 3 micro EV micron squared. So to put this in context, this is almost 3 orders of magnitude lower than the blue shift in gallium arsenide. Okay, so this is problematic if you want to reach a regime such as that of the, such as, for example, the polariton blockade regime. And we can also estimate this value of G in a completely different way. What you could do is resonantly pump one of these lower polariton states without populating your dark states, and then just look at the blue shift of that lower polariton resonance as a function of pump power. And from this sort of measurement, you also obtain a G of about 10 to the minus 3 micro EV micron squared. So all of these values are relatively consistent. Very recently, there was a nice paper by the group of Pavlos Agoulakis, where they carefully measured the blue shift and as a function of pump power, and modeled this by not only accounting for a single reservoir, but also accounting for the fact that you have molecules with a transition dipole moment which is misaligned with the polarization of the condensate, and accounting for energy transfer between the different possible states. And this model accounts now very nicely quantitatively for the blue shift as a function of pump power, and also directly gives you the spontaneous polarization of the condensate as a function of pump power. Okay. So the presence of these nonlinearities leads to a number of important features, one of which is the fact that you have sound-like excitations in the condensate. So this is
Professor?
the excitation. Yes.
We have one question from the audience.
Yeah.
So Said, you can talk now.
Yes, hi, Stefan. I have a question about the magnitude of the line width narrowing in these organic polariton lasers. So in organic photon lasers, as you cross the threshold, the line width can narrow very much, right? I mean, orders of magnitude as you continue to increase the power.
Yeah.
But in these organic polariton systems, all the measurements you showed, there's basically a very, very tiny line width narrowing, right? I mean, it it went in the best case from like 4.5 MeV to 1.5 MeV,
Yeah.
and then it even went up. But the question is why? I think I understand why it goes up again, you know. But the question is why the line width narrowing is so small in these Polariton systems. Yeah, do you have an insight into that?
Yeah, so there are a few reasons, but the very short answer is that in the example you just mentioned, which is, for example, TDF, where I think those numbers come from, this is simply due to the pumping. So you have to compare apples with apples. So if you look at organic photon lasers under impulsive pumping, you'll find very similar line width narrowing. Now, many organic lasers are studied using nanosecond pulses. And there you can see very short or very narrow line widths above threshold because you're limited by the actual coherence time of the emission burst. So if you look at the time dynamics of the TDF Polariton laser, that emission burst lasts for about a picosecond. So if you Fourier transform that in time, you get that 1 MeV line width. So you can't do better than that. You don't get the intrinsic line width from these femtosecond experiments. Does that answer your question, Saeed?
Yeah, I think it does. Yeah.
So if you really cared about the ultimate line width, then you should look at the condensate line width under a long stable pump excitation if you want to learn something about the system.
But even in the quasi-CW experiments that you showed the recent results from Hufling group,
yeah,
it was, I mean, it was longer, as you say, the coherence time, so a smaller line width, but still nowhere close to what you can get for a normal, you know, dye photon laser, right?
So I believe the line width in that experiment is on the order of about 100 micro eV. So yeah, quite comparable to what you would get in a normal photon laser in terms of an organic photon laser. I think that's, I mean, in the best case scenarios, if you don't do anything special, like use a intracavity, like if you use a volume dry grading in an open cavity system, you can get very, very small line widths. But if you just have a regular photon laser, typically we're looking at a few angstrom line widths, so it's quite comparable.
Okay, thank you.
So by the way, Professor, so there are 3 minutes left for the end of the webinar, so if you could please start wrapping up.
Yeah, so I'll finish with these instabilities. Okay. So what was predicted theoretically is that in addition to these sound-like excitations in the condensate, you also have the presence of a dynamic instability, which is due to the reservoir. And this is effectively, why is it unstable? This is a mode or an excitation with an imaginary part, which is positive, so an excitation which grows in time. And there's a condition for the presence of this instability, which is almost always satisfied for typical organic Polariton lasers. So we expect this instability to be present. Numerical simulations have also shown that the size of the pump spot plays an important role in determining whether this instability will exist or not. So for large pump spots, the region of stable condensate formation becomes reduced. And we were able to study this numerically. I'll show these two simulations and then I'll wrap up. So if you come in with, if you excite one of these systems, and these are all parameters known from experiments, with a small pump spot, then you stay in the stable regime. And this, oops, I don't know if I can play this. Okay. So here we come in with an impulsive pump. This is reservoir exciton density. This is the polariton density evolving as a function of time. These excitons are scattering into polaritonic states, and you form this nice stable condensate when you have a small pump spot. Now, if you increase either the pump power or the size of the pump spot, you enter a regime where these instabilities play a role. This is shown here. So now you again have the nucleation of these little puddles of polaritons, but they persist long enough to spatially hole burn the reservoir density. And because you have this positive repulsive interaction, this creates attractive wells for the condensate, and the condensate just breaks up. And if you look at experiments comparing the condensate images as a function of pump spot to theory calculations, you see that the agreement is quite good. And these instabilities clearly cause a breaking up of the condensate at high power. And the same thing is true, this is for large pump spots. And the same thing is true as you increase the power of the pump laser. Okay, so this is nice work showing that dynamic instabilities are important to consider in these organic polariton condensates when you are working with an open system. And then very recent work has studied the formation of organic polariton condensates in confined geometry. These are normally fabricated by etching a little dimple in one of the back mirrors before the fabrication of the actual dielectric mirror. So here you can see the confined modes due
Sorry,
to
Professor.
Yeah.
There is one question from the audience.
Yep.
So yeah, you can talk now.
Thank you very much. I have a question. Actually, do you observe this disorder in the K-space?
So, yeah, so that's a very good question. So in principle, we should see some signature of this in terms of the K-space broadening. It's not something that it's not something that was not something that was really dominant in the K-space data. And one potential reason for this is that most of the K-space data we acquire is averaged over multiple shots. If you average over multiple shots, these sorts of features will completely be washed out because for every laser shot, the instabilities will give you a different spatial pattern. And it looks homogeneous. So an interesting experiment, and I think we would see evidence of these, would be to look at single shot K-space imaging, and I think we would see some K-space broadening due to the presence of these instabilities. So that's an interesting point, and we haven't looked at that directly.
All right, thank you very much.
So I'll just wrap up with this slide. So this is really some of the most recent work that has been done on organic polariton condensates. So of course, single confined polariton condensates were realized, but very recently there's been nice work from the group of Sven Hopfling, where they use this type of approach. So patterning one of the mirrors to create a localized polaritonic molecule, if you will, and arranging these in a 1D lattice to create an artificial band structure here with a band gap, and then looking at condensation at room temperature in one of these lattices. So this is a nice precursor to what is now possible at room temperature with lattices of these polariton condensates. So I'll just move on to the conclusion slide and leave you with some of the future thoughts, which are directly taken from our paper. So at the moment, all of the realizations of organic polariton condensates are highly out of equilibrium. So it would be nice to move closer to equilibrium physics to study elements which are difficultly accessible in the gallium arsenide system. In particular, one of the nice features of organics is the fact that you have a very large Rabi splitting, so we can come in with very large bandwidth femtosecond pulses and not worry about exciting other states, like for example, the upper polariton branch, and study time dynamics. Another question is, well, what is the configuration which will give us the optimal condensation threshold? So we know that vibrational relaxation plays a role, and we have this condition where placing the lower polariton branch 1 vibrational energy below the reservoir helps, but are there other tricks that can be played? Can we exploit some nonlinearities to reduce the condensation threshold? These are questions which are still open. In fact, the weak Polariton nonlinearity is also limiting in a few different respects. Certainly if you want to reach a strongly correlated regime, or if you want to try to do something like create a Polariton blockade, we need to find a way to drastically increase the strength of the Polariton nonlinearity, most likely via exciton-exciton interactions, not a simple ground state bleach. Can we electrically control Polariton condensates? This is an area where work is ongoing. Electrically injecting would be very difficult given the state-of-the-art thresholds, but certainly electrical control is something that it would be possible. And then an area that has been of interest to us, but I haven't talked about, is how to use strong coupling to modify the internal photophysical processes within organic molecules. There's very recent work on studying electrical conductivity of molecules within the condensate regime. So that sort of approach is something which is just being explored since the last years. So on that, I'll end and I'll take any further questions.
Oh, okay, so we have reached like the final part of the webinar. So let me take, we have one question in Q&A, so let me go over it. So this question is from Bin Liu. So it says, does the polarization of POM determine the organic Polariton condensate polarization? Most experiments use linear polarization for POM. How about using circular polarization?
Yeah, so that's a good question. To my knowledge, no one has studied these organic Polariton condensates under circular polarization pumping. One reason for that, okay, so I should take a step back. So one thing to consider is first, how are these systems being pumped? So in most of our experiments, we pump beyond the mirror stop band, and normally there's a minimum in the reflectivity of the mirror only for one of the polarizations. So what this would mean is that if we come in with circular polarization, in the end, only one linear component of that polarization will be exciting the molecules. So under a typical configuration, we wouldn't see an effect. But what you could do is you could try to pump directly through the mirror in a regime where the mirror reflectivity is very high, and then study the effect of circular polarization. This could be interesting in materials where you create some superposition of X and Y transition dipole moments, but this hasn't been done yet. So normally what happens is that the pump component, which is linear polarized, will select some subset of your organic molecules, and this is what will break the symmetry of the system above threshold.
All right, so we are a bit over time. So I was wondering if you are willing to take a couple of questions from the audience, or do you prefer to finish?
Yeah, I've got a few minutes. The kids have not arrived yet, so we're okay.
Okay, so I will pick up two people. So Gilad, go ahead.
Yes, so I have a fairly general and perhaps a bit naive question. So you increase the number of excitons in the cavity by increasing the pumping power, but organic molecules usually can also be pumped to higher excited states if you increase the pumping power. So is this playing any role at all in the dynamics?
So what do you mean by higher excited states?
Well, a molecule can go to the second, third excited state depending on how you excite it. And
so this wouldn't be so much the pumping power, but the pumping energy. So in a lot of our...
No, because after you pump to the first excited state, if the molecule is already staying there, you can excite it again to the second excited state if your pulse is long enough, let's say. So yeah, I guess that might depend on the pulse length as well.
Yeah, so in, let's say for the range of parameters where we work, this is a very unlikely process. In some cases, we actually directly excite, for example, in the second excited singlet state, S2, we just use this as a tool for quickly and efficiently populating the dark states, because we don't want to pump directly where the mirror is, because the DBR is very reflective. So we go to high energy beyond the stop band, directly pump the second excited state where the absorption can be very high, and then rely on relaxation from S2 to S1 being very efficient to create our initial population. But just directly pumping S1, we're certainly not in a regime where we can efficiently populate S2, except that the small caveat to that is that we do have bimolecular annihilation, and that can involve some quick excitation to S2 followed by very fast internal conversion, which leads to the loss of some of these excitons. So in that sense, it's a lost process.
Okay, thank you.
And so we have one final, I will just choose one final quick question. So, so Pedro, please, one quick question.
Yeah, hello.
Hi.
It's a short question on, can you make a general comment of the possible effects of a TADF system for condensation, like the possibility to have condensation in a TADF system?
Okay, that's a very interesting question, and one that we're actively looking at the moment. So I didn't talk about more recent work on TADF and TADF polaritons, but an interesting situation would be one where you have, for example, a TADF material, where you can have, first of all, if you have a TADF material, you normally have a small exchange integral, which means that the singlet and triplet are very close in energy. So in this sort of geometry, it's possible to push the lower polariton branch below the triplet state. And then the regime, which would be really interesting, is one where you form a condensate in this lower polariton and activate stimulated scattering from the triplet to the singlet condensate. And this is something that has, as far as I know, not been demonstrated, and certainly something worth investigating and something we're looking at.
Okay. Thanks.
All right. So for the sake of time, I think it's a good idea to finish the event, since it seems that many people are leaving the webinar now. So just to wrap everything up, thank you, Professor Stéphane, for the interesting talk. And on behalf of the audience, we sincerely appreciate you being part of this webinar series. Today we hosted 156 attendees, and we are happy to see the participation of the community in this series. So just one quick announcement before we go. So Professor, could you stop sharing your screen so that I can share mine? Let's see. All right. So just for your information, next week we will have Professor Prineha Narang from Harvard University as our next speaker. So remember to register at the link shown here if you wish to attend. And finally, I just want to extend, well, I just want to thank everybody again and for your attendance, and stay safe and healthy. Thank you.